Okay, from now on, I'm gonna give you a little bit of little bit of lower level for the models. I'm not going too deep. So if just follow me, and if you cannot get it, it's fine. Okay. Okay, the first machine learning model. This is the simplest one, I say. So we have a data set, two-dimensional data set. And then I use the linear classifier. And what it does is finding the line for predicting the classes, let's say. And okay, we got these lines. They are all right because it can divide our training data set perfectly. So these black lines are all good, all perfect, 100%. But there's an issue. As you see, we have these unknown data set for test. But then, okay, this linear classification get me a different answer from this one. And same goes to this one. Like, I don't know, like this around this line, they give me different outputs based on their training model. But it shouldn't be like that, right? We want to have near constant prediction all the time. So someone got that issues there, and then they solved the problem with the new model called support vector machine. So what it does is similar, just finding the line, but they are not randomly stopping whenever they've done the training, but they still try to find the best maximum margin hyperlink. So just pushing, and then find the best line in the center. So it'll give you the same training model all the time based on your training set, which is excellent, and it really gives you a good performance. So it's simple algorithm, but still really used in many machine learning areas. They're really good. And this is the algorithm we will use for the stock prediction as well. Okay. And the logistic regression, this is another machine learning algorithm. This is the key concept for the neural net. So this picture say, oh, I'm gonna predict my data sets if it's belonging to the class 0 or the class 1. So it's the classification algorithm. I want to predict which one, the 0 or 1. That's all I'm doing. And so as you see this S-shaped curve, that's what we call for the activation function. So what it does is, let's say I have a data, and this regression, the logistic regression will give you a number between 1 to 0. And what it is actually the probability to be my class y equals 1. So that's the probability they throw. So that's why it's the range between 0 and 1, which means, all right, I gave my data set around here. So I got, at the end, the logistic regression throw me this one. So it's about like a 0.8. And what it means is, oh, this 0.8 is the probability that I can predict my data set to be the class 1. That's the probability. And so, okay, I'm 80%. So I say my class, the data set has a class 1 because that's what probably they got me. And similar to this, so I have a data set here, data point around here. Then my logistic regression give me like a 0.1. And then that means that's the probability that my data set belongs to a class 1. So this probability is only 0.1%, which isn't great. So I would say, oh, mine is actually class 0. That makes more sense. That's this logistic regression. Okay, I hope that's not too bad. So why is so important? I don't know, because that's the main key algorithms we use for the neural net. Neural net is the nearly one key algorithm in machine learning. So we must understand this a little bit. So, all right, it looks like something. So I'll spoil a little bit here. So that's the neural net when we are talking about in machine learning. So our kind of wire everywhere here and there and connecting nodes, that's the neural net. But in here, just from the data set, the input data towards the node, you see this part, each node actually represent this guy. So each one is getting the input from the last node or just from input. And then they give you the prediction, the probability. That's all they are doing anyways. So, all right, I thought the machine learning, the neural net was so complicated, so I couldn't understand. Actually, it's so simple because at the end of the day, what you get is the linear algebra. Just the combination of the linear algebra and then plus the constant b, the bias, we say. And okay, so you have this one, this formula, simple formula. Then that's the value you feed to your activation function here. So this activation function will give you a value between 0 to 1, the probability. That's it. That's all you need. You just got the logistic regression and neural net. Okay, so the neural net, this is the most basic neural net we talk in machine learning. So why we call neural net? It's like a biology kind of science term, no? Actually, it is, but the way it looks like is very similar to our brain neurons and the way they communicate. So they send the electrical signal to each neuron, and then at the end I can move my finger, you know. So yeah, this architecture looks very like our brain neurons. That's why we took the name a neural net. We know what's behind it. This is all the logistic regression, the simple, the linear algebra here. It's fine. So what's the aim? What are we doing with this algorithm for the machine learning? All we do is say, you see this constant, the W, that's what we call weight. And this B constant, this is what we call the bias. So we want to find the best value for these variables. That's all we do. So that's the only reason we train like 1,000,000 times to get the best number for them. So yeah, it says, yeah, we are doing training because we need a good weight value. Fair enough. And at the end, what you get is the predicted value. Right, that's good. Any questions so far? It was pretty heavy.
Yeah, it looks a bit scary. But I think like machine learning in general is about the same concept. Is if you take like the simplest regression problem, let's say equation problem, y equal to a1 plus x1 plus b. All we have got is just like one x1 variable, and then we are trying to find the constants, which is your a and b. And once you know a and b, you can have like as many inputs you want to predict the output. But if you expand the same idea in the neural net case, where we have got fully connected layers, and you've got, let's say, hundreds of features, input features, and they've got like 2 or 3 hidden layers, the same problem become quite complicated because now you are dealing with hundreds of. All you got to do is like, again, the concept is pretty much the same, that find the constants, which you call the what's called the hyperparameters in your
Mm-hmm.
in your hyperplane that we are trying to find, which is just nothing but constants, and you're trying to find the best values for these constants for which you can predict the value y for input x, set of x. And I think this is what we're trying to do here. Each layer would have like the weights w1 to wn, then bias. So for n variables, n features, we are like n plus 1 in each layer, and then the second layer we have like some weights in between the first layer and the second layer as well. So there's sometime, I think there's like billions of the last machine learning model, the latest models I've seen, they've got billions of weights to train.